Morning student, I am NV Krishna Rao, Assistant Professor in CSE department. I am handling the subject compiler design for the 5th semester. In the last class, we have discussed with the phases of a compiler and we have seen one example by how which each phase of a compiler will convert the source program to target program. Now we are discussing with one more example. Here our example is position equal to initial plus rate into 60. Here the position, initial and rate are float type and the 60 is integer type. So this is a single statement in the high level language program and we'll see one by one each phase is converting. Right? The first phase, lexical analyzer. What is the task of the lexical analyzer? Read each character by character of the source program and construct the lexemes and follow the pattern rules of the programming language and generate a sequence of tokens. So this lexical analyzer, whenever it sees the variables, lexemes, it will store its respective information in the symbol table. So first it will read the lexeme, a sequence of characters, that is position. That variable position is storing in the first entry of the symbol table. So it generating a token id comma 1. Then the next lexeme is assignment. So this assignment operator is stored in the operator table and it will generate a token operator. Then our third lexeme is initial, right? Our third lexeme is initial. It will be the initial. Here this lexeme is stored in the symbol table with the record number 2 and it will be construct a token with identify type and its a symbol table record is 2. Then plus sign is an operator. So simply construct its respective token. Then identify 3 rate. The lexeme is rate and it stores into the symbol table. That rate is stored in the symbol table and it generates a token id comma 3. It generates a token id comma 3. Right? Then multiplication. Multiplication is an operator. It will be generating a token with multiplication. That is a token generated. Then another one is integer. So lexical analyzer simply construct a token 60. Right? The output of the lexical analyzer is a sequence of tokens. Identify 1, assignment operator. Identify 2, addition operator. Identify 3, multiplication operator and a number 60. Lexeme is a sequence of characters are grouped to a tokens. A group of lexemes as token, as identifies, as keywords, as numbers, as operators, like that. It will classify the lexemes into a sequence of tokens. Then output of lexical analyzer is a sequence of tokens. This sequence of tokens is the input to the syntax analyzer. Right? It will be the input to the syntax analyzer. What is the task of syntax analyzer? It will follow the syntax rules of the programming language. And the syntax rules are represented by context-free grammars. Right? The syntax rules of programming languages are represented by context-free grammars. This syntax analyzer will follow the syntax rules and it groups the tokens into the syntax trees or parse trees. This is the syntax tree or parse tree. The task of the syntax analyzer, it follows syntax rules represented by context-free grammars of the programming languages. Using them, it will group the sequence of tokens. It will group the sequence of tokens into a syntax trees or parse trees. The output of the syntax analyzer is a syntax tree or parse tree. Right? It simply checks only the syntax rules. This output will be the input to the semantic analyzer. The third phase of our compiler design is semantic analyzer. The semantic analyzer will check this express statement will be executed properly or not. Any modifications it required, it try to perform them. Further it is unable to do, then it will generate the error messages. Error handler will handle these errors and convert to suitable sentences, and it will be generated out to understand by the programmer or user. So what this semantic analyzer do? All the three variables are float type. Then if we consider the multiplication operator, it has one is float type, one operand is float type, another operand is integer type. So it will take the conversion of integer to float. It will take the conversion of integer to float and it will perform the float multiplication. It will take the conversion of integer to float and it perform the float multiplication. Then float addition and float assignment will be taken, operations will be taken and the statement executed properly. The task of the semantic analyzer automatically convert the integer to float such that the statement will be converted to abstract syntax trees and it will pass it to text phases without any disturbances. The source program will be converted to target program by each phase of a compiler. This abstract syntax trees will be the input to the intermediate code generator. It is the input to the intermediate code generator. It is a bridge between analysis phase and synthesis phase. It is a bridge between analysis phase and synthesis phase. It converts the abstract syntax trees to one of the intermediate form. Example is 3 address code. So here it is converted into 3 address code. That abstract syntax tree is converted into the 3 address code where T1, T2, T3 are the temporary variables. So each operation is represented, that expression is divided into simple operations and it will be represented by each statement. So the single abstract syntax tree is divided into 4 statements of the intermediate representation by intermediate form, that is 3 address code. This 3 address code will be the input to the code optimizer. It will be the input to the code optimizer. What is the task of this code optimizer? To optimize the tree address code such that it will have less number of statements, takes less space, so that execution will be faster and it should be efficient. The output of the code should not be changed, but make them execute faster, takes less space and more efficient. That is the task of this code optimizer. This code optimizer is an optional phase in the phases of a compiler. Depending on the programming languages, we use this code optimizer. Right? This output of the code optimizer, optimized intermediate code, will be the input to the code generator. It will be the input to the code generator. This code generator will convert this optimized code into respective code generator. The optimized machine code intermediate representation, optimized machine intermediate representation is converted to machine code by the code generator. The code generator is the final phase of the compiler which takes the input optimized intermediate code which will be converted to the final machine code. So here this is the final machine code generated for the optimized intermediate code, right? So this is a one example which converts the source statement in high level language to machine level language. Okay, this is a one more example. Here, what is the statement? A of index equal to 4 plus 2. We are storing the summation of 4 and 2 into an array. Index should be integer type. Now we'll see how this source statement is converted by each phase of the compiler, so that finally it will generate a machine code, right? The first phase, lexical analyzer, right? The first phase is lexical analyzer. So what is the first lexeme? A. A is a lexeme. What is it? It's a token. It's an identifier. Then what is the second lexeme? Left bracket. Third lexeme, index. It is an identifier. So that these identifiers A and index will be stored in the symbol table and a tokens will be generated. Identifier followed by record entry of the symbol table. Then next lexeme is right bracket. Then next lexeme, assignment operator. Then next lexeme, a number. Then next lexeme, plus sign, addition operator. Next lexeme is a number, right? So here the task of the lexical analyzer, read the character one by one and consider that lexeme and convert to the tokens, and it will be the input to the syntax analyzer. It will be the input to the syntax analyzer. What is the task of the syntax analyzer? It follows the syntax rules of the programming language which are represented by context-free grammar protections. Using them, group this sequence of tokens into a syntax tree or parse tree. Here, these tokens, A, index equal to 4 plus 2. this is a syntax tree or parse tree. Following the syntax rules of the programming language, it is generating the syntax tree. Right? So, what is our statement? A of index equal to 4 plus 2. Then here the syntax tree is generated. Right? A sequence of token which is output of lexical analyzer will be the input to the syntax analyzer, which results to the syntax tree. This resultant syntax tree is the input to the semantic analyzer. Semantic analyzer. Right? Here it will check the types of all the operands for all the operators are matches or not. 2 is an integer, 4 is an integer, index also integer, identify A is array of index, array of integer. So it is in proper way. So it doesn't require any semantic conversions. Right? So the semantic analyzer will check the execution of this statement. It will be properly executed or not. Right? If it is in the proper way, it won't perform any modifications, and the abstract syntax trees will be the input to the intermediate code. It will be the input to the intermediate code. What is the task of the intermediate code? Convert these abstract syntax trees to the intermediate form. Convert into the intermediate form. One of the intermediate form is 3 address code. Right? So here this expression is converted as t equal to 4 plus 2. The t is a temporary variable. The temporary result is assigned to A of index. Right? This abstract syntax tree is converted to a intermediate form t equal to 4 plus 2 and A of index equal to t. Right? This intermediate form yields the input to the code optimization. The task of the code optimization is that reduce the size of the code so that execution will be fast, and make the statement more efficient so that output is more accurate. Right? So that is the task of code optimization. Right? Then code optimization will convert this intermediate form as t plus 6, t equal to 6 and A of index equal to t. So the number of operations are reduced. Here there are 3 operations in the intermediate code. Now modified as only the 2 assignment operators by optimizing by the code optimizer. Right? We are minimizing the number of operations. This optimized intermediate code will be the input to the code generator. It will be the input to the code generator. Further, optimized A of index as 6, right? This A of index 6 is the input to the code generator. So finally, what is our optimized intermediate code form? A of index equal to 6, right? A single statement. This single statement is converted to our machine code. Assembly language programs are machine instructions. Further, there are some optimizing methods also available in the code generator to optimize the resultant assembly language program. So, the 6 statement assembly language program is converted to 3 statements of the assembly language program. We will have the separate code optimizer. Then also we will use some optimizing methods in the code generator to apply on the machine code or assembly language statements. So here the optimized single line A of index equal to 6 is converted to 6 lines of the assembly language program. Further it is optimized to 3 statements of the assembly language program. So it is final phase of the our phases of a compiler, right? It improves the target code generated by the code generator by address modes choosing or instructions replacing or redundant eliminating. These are the different optimizing methods that we use in the code generator. So later, while we are discussing the code generator, we'll discuss these optimizing methods one by one. So these, what are the addressing modes choosing? There are different addressing modes. So which one is better for our resultant instructions? Then instructions replacing. We have 6 statements are replacing with 3 statements. Redundant eliminating. If any statement is repeated with the same result, instead of writing multiple times, we write only at one time. Right? So here the final optimized assembly language program is generated with 3 statements, which is the output of our source program, a source statement, and it is converted by each phase of a compiler, right? So A of index equal to 4 plus 2. Then lexical analyzer will construct tokens for each lexeme. It will construct a tokens for each lexeme, right? Then these tokens are the input to the syntax analyzer. The syntax analyzer will construct the syntax trees from the sequence of tokens, right? Then the output of the syntax analyzer, syntax tree or parse tree is verified by our semantic analyzer. If the types of all the operands are matching, then it properly passes to the next phase. Here 2 is an integer, 4 is an integer, and index is an integer, then array is an integer type. So it verifies and passes to the next phase intermediate code. Then it will be t equal to 4 plus 2, A of index equal to 2. This intermediate representation 3 underscore is converted to, it is passed to code optimization. The code optimization will try to reduce the number of operations, number of statements, so that resultant code is more efficient. So finally we get A of index equal to 6. A of index equal to 6. The optimized intermediate code. It will be input to the code generator. It will be the input to the code generator, right? Then task of the code generator is convert this optimized intermediate code to the assembly language and machine level language forms. So the single statement of optimized intermediate code is converted to 5 lines of assembly statement. It is converted to 5 lines of assembly statement. This is the resultant assembly language program. But in the code generator also, we will apply some optimizing methods such that we'll get a minimized, efficient assembly language statements or machine code statement. So finally, we get only the three statement: target code optimization, target code optimization. So in the code generator also, we'll have different optimizing methods to improve the target code so that execution will be more faster and more efficient. So choosing the correct addressing modes or modifying the addressing modes or instructions replacing or eliminating the redundant statements. So if the same statement giving the same output at multiple places, instead of evaluating the statement, we use the result. So that is eliminating the redundant eliminating. So these are we are seeing the examples of how the compiler phases will convert source program statement to the target program, a machine or assembly language program. Right? So in the next class, we'll discuss the symbol table and other handler, what is its purpose and uses, how they are interact with our phases of a compiler. So for today, I'm closing this section. Okay?
Like, share and subscribe. Hit the bell icon for more updates.